Hello, and welcome to C++ 20 templates, the next level, concepts and more. I'm Andreas Fertig. I work as a trainer and consultant for C++. I'm the author of C++ Insights, which we will not see today. Instead, we will see Matt Godbold's Compiler Explorer. Really funny. And well, enjoy the presentation, have fun. If you like to ask questions, please refer to the Q&A section. I will answer your questions at the end of the talk, and I will go through the Q&A there. This also allows you to upvote or downvote questions such that I can see which is the most interesting one. Okay, let's see where this thing is working here. Perfect. All right, so first things first, my last name is Fertig, and that's a German word. That's a very common German word. You can translate it to finished, ready, complete, or completed. So you can see that it's commonly used in sentences. For example, I just finished the project. Ich habe das Projekt fertiggestellt. So the word fertig is used a lot there. It's an adjective in German, so that means that we spell it with a lower first letter, but as my last name, it goes with a capital first letter, and that makes me constantly fight with the spell checker because it cannot detect the context whether I refer to my last name or I'm saying that something is fertig. It's a really interesting word I started thinking about lately because it depends on the meaning depends on how I say it. So for example, if I say, ich bin fertig, that's like, oh, I'm totally exhausted and I'm finished. But if I say I'm fertig, then the problem means, hey, I finished something and I'm really happy. And it's hard to detect that. You have to see the emotions. But enough about German. Let's talk about C++, my probably third language. Concepts. So what are concepts? Concepts allow us to formulate requirements for a type. Okay, it's the first time we can do this in C++, and it's quite great. You can, if you want, you can compare it to std-enable if. But std-enable if does only a teeny tiny portion of what concepts can do. But this is a portion we will see and you can compare it to. Concepts themselves, they consist of the definition of a concept where we have a new keyword for, namely concept, and requirements, where we have another new keyword for requires. And we will see this in a lot of places. So concepts always consist of requirements. And the figure in the middle of the slide illustrates how we build a concept, or technically from the specification. So concepts are meant for generic code. That means they always start with a template head because it makes only sense with generic types. So in this template head, you can use anything you already know from function or class templates. Okay, you can use type or non-type parameters and even template parameters, but that's a more tricky section. After the template head, we start with the new keyword concept. This tells our colleagues and the compiler that we are looking at a concept. And then we give this concept a name. We have to follow the usual variable name rules here. I chose my concept. That's a really great name, I think, for a concept. It's probably unique as well. And then after the equal sign, I'm assigning requirements to this concept. In my case, I use another concept, stud same as, which comes with the standard library in C++ 20, and stud is class v and stud is enum v. The last two ones are type traits. So the requirements, they must yield true or false at compile time. So we can use either a concept or a type trait or anything that's evaluatable at compile time. And then we can use Boolean algebra to combine these various requirements we have. And in my example, I use and or to group them together. Okay. So this is a high-level overview on how the concept definition looks. Let's start with an example. Say I have the requirement that I want to write a function called add. On this function, it should take an arbitrary amount of parameters, all of the same type. This is the requirement. No mixed types. That means that on this slide here, line number 1 and 2 both should compile. So I should be able to call add with 2, 3, 4, and 5, as well as with only 2 and 3, and any other combination of the numbers. But it should fail compiling when I call it like in line number 3, when I call add with 2, 3, 3.14, because now I'm mixing integer and floating point types, and that should lead to an error. Okay. In principle, we like to have a way to later add the overload which handles floating point or mixed types in general. So we are looking for a solution where we limit this add function only in its function signature, so without using a static assert. Okay. And from the signature, you can probably infer we are talking about a variadic function template at this point. And let's start with the C++17 version first. This is my solution in C++17. The grayed out part at the top, these are two helper type traits. They're not that interesting, so I will briefly walk you through. The first one on line number 2, it's called rSameV. It uses C++17 stood conjunction V together with stood is same to check whether all types in the parameter pack are the same. Okay, and the second helper is first argt. It also takes a parameter pack like my rSameV, and it uses this internal helper struct in line number 5, first arg, and all it does there practically, it splits up the first parameter from the parameter pack or the type from this parameter pack and provides it inside in line number 6 with a using, and in line number 10, my first argt, the using alias referring to this type. So essentially first argt gives me the first type from a parameter pack, okay? And because I have rSameV, I make sure that all types in this pack are the same. So whether I grab the first one, the last one, or something in the middle, I will always get the same type because they are all of the same type. And then in the not grayed out part at the bottom of the slide, we see the implementation. In line number 1, we can see it is a variadic function template, no surprise there. It says type name ... and I name this parameter pack args. And then in line number 3, we can see, yes, the function is named add. It takes this parameter pack, and in line number 5, I'm using a full expression from C++17 to expand this parameter pack and apply the add operation to it. Okay. So far, so good. The interesting part is line number 3, because the return type is missing. And that's in line number 2, making line number 2 even more interesting. There I'm using a stood enable if t. So this is the premium version of enable if because it spares us writing type name in front of it, but we still have to write this enable if t. And then we see our rSameV as the first argument to enable if t and first argt as the second. Now you have to know, and some of you surely do, that the first argument to this enable if is the condition. So this returns true or false, and if this condition returns true, then enable if returns the type in first argt as the type here. And if not, we are looking at SFENI, so substitution failure is not an error, and we are unable to instantiate this function add. So either it comes with the return type in first argt, or add itself isn't there. This is how this works. And I'm not sure whether you already noticed, you've heard it for the first time, or you forgot about it. I remember when I learned it back in the days, it wasn't easy. And all the time when I teach things like that, I see that people take it as it's still not easy. Okay, if you get to this point the first time, then you see a lot of these angle brackets. It feels different. You don't see the return type. It looks odd. It's not regular code. So this makes it very hard for starters in C++ to reason about this code, not talking about writing it yourself. Okay. So C++ 17, it's good because it enabled us to do what we've done in the past, but now we have C++ 20. And C++ 20 allows me to come up with this solution to the function add. Line number 1, we are still looking at a variadic function template. Line number 4 looks much better now. Audio as the return type is back. Other than that, I see it's the function add and the rest of the signature is totally the same as before. Line number 6, C++ 17's fault expressions, nothing new going on there. The really great improvement here, that's line number 3. In line number 3, I now say requires are same we. I still need my helper type trait. I implemented in the C++ 17 version already, but I only need are same we and requires. The enable if is gone, this construct that's really hard to read and that masks my return type, that's gone. I can now express this is a requirement. All types in this parameter pack must be of the same type. And I say this with the keyword requires. Okay, this is readable. You may have to look up what rSameWe does, what's the implementation behind that or something like this, but the rest, that's crystal clear. And this is the improvement from only one part of C++ 20's concepts. This is only the requires clause. Okay, so there's more to concepts than just using the final concept. But this is an illustration of how powerful concepts are in C++ 20. And while we are speaking at that, here are the various application areas for concepts in C++ 20. We are now able to replace in the template head type name or class with a so-called type constraint, with a concept. So upfront, we can state that a certain function template, class template, or whatever template you have takes any type which satisfies a certain constraint. Okay, we couldn't formulate that before. We had to put enable ifs in default parameters, maybe static asserts, but I was never able to express this upfront. And now I am. I can say this in the template head. And there it only works for concepts that take a single argument as a parameter. So once we have concepts that take multiple parameters, we can use the requires clause. This is the one we previously saw in the add example. There I can use either concepts or type traits. Once again, must be yield true or false at compile time. And there I could use concepts taking multiple types. For example, if I have a template that takes 2 types and I like to ensure that they are both the same or something like this, or convertible to each other. Then in C3 and C4, we are seeing a way to constrain so-called placeholder types. So we have audios in C++ 11, and you can read C3 also like a variable declaration. Here it's the return type of this function fun, but you can in the same way constrain your variables as well with a concept here, with a constraint to the placeholder type. Okay, C4 practically is the same thing. You can read it either like the return type or like a variable, but here we see something that's partially new. We are seeing auto as a parameter type. And prior to C++ 20, this was only allowed in generic lambdas since C++ 14. But now we can use them in other places as well in irregular functions. We will see an example for that, which is called abbreviated function templates later. Okay, but these are both constrained placeholder types, and we can constrain them now with concepts. And then the last one is the trailing requires clause at the end. And there we once again initiate that with the keyword requires, and then we can use either concept or type traits. And in both the requires clauses, we can use Boolean algebra to combine the requirements we have at this point, okay? Now, if we think back about the add example, we can say that we already figured out one requirement. That's the one I told you about. Let's call that requirement A, and this is that add should prevent being called with mixed types. But that's only one thing, and it's probably one of the easy ones. But add has a lot of more requirements. So let's say we have the requirement B, add can, without making much sense, be called with only one parameter. The name of the function is add. If I call it with one parameter, there's really nothing to do for this function. So it's a waste of CPU cycles. So let's prevent add being called with one parameter, okay? You may have an application where you're in highly generic code, and then you might say, okay, it could be that I end up with only a single parameter, then all right. But for this example, let's say add must be called with 2 or more parameters. And then our requirement C, which is much less obvious, the type used in args must support the plus operation. It's only a single line, the implementation of add, so we can quickly spot it. It's much different in your real world code. But even here in the single line function, it's hard to see or understand, combine whatsoever, that the types we are putting in must provide an operator plus or a plus operation. It's sensible because function's name is add, but we could also have chosen to say, well, we want that our type provides a function called addition or something like this. And then that would be hidden inside of the body of the function. We cannot see it up front. We have to look at the implementation. Fairly easy with a one-liner, but we have to do it. A possible requirement D is the operation plus should be no except, because add all the time was no except. I didn't talk about it, but if you go back to the slides, both add versions in C++ 17 and 20, they were no except. And because I mentioned that I mostly add integer or things like that together, I don't want to place a try catch around it. So let's say that we like to verify that operator plus is no except. And then as a last requirement, E, the return type of the operator plus should match that of args. Okay, so because we are free implementing operator plus, we technically can return a different type from operator plus than we pass into it. Totally different type than our classes. And we don't want that. For consistency reasons, operator plus should return the same type as it was called for, okay? So a couple of requirements, not all of them are easy to check in C++ 17. So let's see how we can do that in C++ 20. But before, let's look at another element of concepts, and that's the requires expression. I often read the requires expression or think about it like a function. Function with the name requires, which doesn't have a return type, so maybe like a constructor, okay? Always named requires, and then I have the parameter list. The list can be empty or I can fill it with parameters like I'm pleased to. I can use all types that are already available because we included them, like maybe if we included std_string before, then we can use that. We can use built-in types, integer and so forth. And we can also use template types that are coming from the concept or from the function template, which they are used in. And these parameters are used only inside of the requires expression to well, enable us to write more usual code. We will see much later an example about how powerful this is, but you can do anything here. You can say that it takes a reference to T, a pointer, const. You can go crazy with east and west const things. So the type is never used at runtime. It's only used at compile time to determine whether this requires expression yields true or false. So whether the requirements are met or not. Okay, and this is the purpose of this parameter list here. And I can use these parameters later in the body. And that's the idea. Now, the requires expression itself comes with a single requirement, and that is that the body of the requires expression must have at least one or multiple requirements. Okay, and we will see these requirements on the next slide. But first, we're now looking at the requires expression. Previously, I showed you the requires clause and the trailing requires clause. And we can say that the requires clause on the previous slides, C3 and C5, that's a Boolean expression. And the requires clause can be seen as an if that evaluates the Boolean expression, and the requires expression returns such a Boolean value. So here we are looking at the value provider, and in the requires clause, we have something that checks this requirement for true and false. Okay. So inside the requires expression, we can use 4 different kinds of requirements: a simple requirement, a nested requirement, a compound requirement, and a type requirement. The 2-letter abbreviations here I will use later in the code to refer to them. And for our add example, only the first 3 make sense. So I will show you the type requirement later in a different example. Okay, so these are the 4 requirements or requirement kinds we can use in a requires expression. So let's start working on the requirements for add, implementing them. So we start simple with a simple requirement. The purpose of a simple requirement is to check whether an expression is valid and will compile. So we start in line number 1, our requires expression. We use the parameter pack args here that we have it handy. And in line number 3, I'm using the fold expression, the same I use to implement add itself. So that's a repetition I don't like, but that comes from my example here. And I simply write this fold expression. The compiler will now, for a simple requirement, try to expand it at compile time. If that succeeds, then this requirement is met. If it doesn't succeed, then this requirement fails and the entire requires expression returns false. So this is our requirement C. We are now checking that one. And at the bottom of the slide, you can see that I'm creating here a struct called noAdd, which obviously comes without an operator plus. And if I now start calling add with 2 instances of noAdd, my requires expression will yield false for that parameter combination. Okay, so we can check our requirement C. That's checked now. Which brings us to the next requirement, the nested requirement. And that one is a little bit tricky. What it does is it evaluates the Boolean return value of an expression at compile time. All these things happen at compile time. Line number 4 and line number 5 are nested requirements. And the tricky part is that you have to put the requires in front of the following expression, of the expression that follows. So in line number 5, if we look at this size of ... args greater than 1. So this is to check whether in my parameter pack are there at least 2 or more elements. And without the requires in front, we are looking at a simple requirement. And this is the tricky part here, because without the requires in either line number 4 or line number 5, let's say line number 5, I'm only looking at size of ... args greater than 1. And as a simple requirement, this would always yield true, because args is a parameter pack. I can apply the size of operation to it, and whether the result is greater than 1 or not, that's not part of the check of a simple requirement. It only checks is this instantiable. And the answer would be yes, even for 0 arguments in the parameter pack. If we put the requires in front of it, we force the compiler to evaluate this expression and get the value. So here we are querying the greater than 1 result, true or false. Okay. So it's important for a nested requirement that we need the requires in front of it. And this enables us to check our requirements A and B. So all types in the parameter pack are the same. That's checked with line number 4. And line number 5 checks that our parameter pack contains at least 2 elements. Below is, once again, the code that illustrates what no longer works. I can no longer call add with 2 and no add, and I can no longer call add with simply the integer 2. So good. Now let's look at the third requirement, the compound requirement. A compound requirement checks the return type of an expression. And it can do 2 things. And in line number 10, I'm showing the 2 things at once. So a compound requirement always starts with the curly braces with a scope or with a compound statement. And in that, we once again see the repetition of my fold expression. I don't like that, but it's due to the small example. And after the compound statement, we can see the keyword no except. And this is the first check that we can do with a compound requirement. This no except tells the compiler to check whether the expression in the curly braces is no except. And by that, we are checking whether operator plus is no except. So is this result, is this entire expression, is it no except? And then after no except, we see something that looks like the trailing return types error. And you can read it the same way here. And it points to a concept. At this point, we must use a concept. And here I'm using C++20's same as. So it checks whether 2 parameters are of the same type. Okay, 2 parameters. And I know there are a lot of angle brackets, and it probably takes a while to go through them on your monitor. But at the end, you will realize that I'm currently passing only 1 argument to same as, which makes only little sense, right? Because it should compare it to something. And the answer to that is the compiler is able to fetch the resulting type from the compound statement, from the curly braces expression, and it feeds it in as a first parameter to same as. Okay, that's a really cool thing we have as a new ability from the compiler in C++20, that it can fill the first parameter in here, making my same as concept valid, because now it's being called with 2 parameters. And this is the version where I do 2 things at once. I'm checking for the no exceptness of the operator plus, and I'm checking whether the result is the same as my first arg t. You can do this in 2 steps. That's what in comments line number 8 and 9 shows. You can simply only check for the no exceptness of this expression, or you can only check for the return type of this expression, okay? Now our remaining requirements D and E are checked as well. So all our requirements for add are now checked. That's great. Now let's piece the pieces together. And one way to do this is starting with an so-called ad hoc requirement. An ad hoc requirement you're looking at if you see the sequence requires, like in line number 2. The gray part here is the requires expression we did build on the previous slides. Okay, that's why it's gray. You already know that. And line number 1, that's the well-known template head from our variant template. Line number 9 and to 12 down, this is the implementation of my function add. And now I'm attaching this requires expression here. And because this is the expression, and the first, the blue requires, this is the requires clause. So this is the if that evaluates this following expression. This is why we need the requires here. And Now we have what we want. But what we also have is a first sign of a code smell. Because of this requires. Think about how much time we just spent on building this requires expression, okay? That's some time, and it will always be that way. These are requirements, so we have to be careful piecing them together. But now we did put it in one place, and all we can do is now copy and paste it around, which for sure is the worst idea we can come up with. Okay, so this is why this is the first sign of a code smell. We spend so much time, and now we can use it only in one place, in one single place. And that's probably not good. For this example here, you can argue that it's so highly specialized, maybe it's best that it's only here. But let's say, no, we want to be able to reuse it. So what we do is we attach it to a concept instead. So in line number 1, we see the template head, but then in line number 2, we see our first own concept definition. I started with the keyword concept, I call this thing edible, and then after the equal sign, I assign the requires expression to it. It's a grayed out part because it's still the same that we did build before. And now, if you look down to line number 10 to 15, in line number 11, we can see the requires. So this is the requires clause. And this time, I'm checking the edible concept. This makes this function add for me also a bit more readable because the previous version that was a lot of code in between the template head and the actual function. Now I moved that to a different place, but it's also reusable. I can use this edible concept in different places, and that makes it more valuable, especially in your day-to-day business with real-world code. You want to reuse these things. And while we're talking about real-world code, we probably should test that thing, right? Because it's a core component now of this function, our concept edible. And here's my approach of testing the created concept. I'm creating myself here a stub. It's the struct in line number 3 is also called stub. So it's a stub. It's also a template taking 3 non-type template parameters, one for no except, the other one for operator plus, and the last one for valid return type. And then inside all that thing does is either it does or doesn't provide an operator plus, which either is or isn't no except, which either returns the correct type or it doesn't. Okay, all that configured with non-type template parameters. And of course, the trailing requires clause here in line number 11 and 6. And for easy later use, because I cannot really remember whether stub true is a valid class or not, I'm creating in line number 16 to 19 myself a couple of nice naming or spelling talking to me using aliases like no add valid class, no except, and different return type. And the good news now is we do have all together we need to test our concept. With this stub, we can simply use the built-in testing framework into the compiler called static assert. Concepts are compile time things, so I can test them in a static assert. And with my stub, I just created myself one thing where I can create a different variations of I need to test it. So in line number 2, I don't even refer to the stub. I call the concept edible with 2 different parameters and ensure that it yields false. I also then in line number 5 call it with only a single parameter, ensuring the same. And then down in line number 9, I'm using it with valid class, in line number 10 with no add, and so forth. So this is how you can test your concepts. You don't need a new testing framework for it. We have it all built in. Okay, we just have to do it, and it's important. So this is about how to create and how to test concepts. Now let's move on a little bit to function templates, more specifically to abbreviated function templates. This function do logged here, it's a pattern I regularly use and like very much. What I do in here is in line number 4, I'm acquiring a global mutex with a lock guard, and then in line number 6, I'm executing a function in a now locked scope. Okay, so I prevent that this code sprinkles into the entire code base. I can change the mutex, I can change the way it's locked, or maybe I can even remove the lock if it's in a different scenario no longer needed. All people have to do is call do locked and be safe that everything is executed in a locked context. But two things are bothering me at least a little. One's more, one's less. Line number 1, the template head, it has the same amount of characters than the declaration of the function in line number 2 itself. That looks not so nice for such a short 6-line function. But the second, more important one is, if we look only at the signature in line number 2, it's hard to interfere that f must be a callable, a function pointer, a lambda, something that's invocable, because that's what we are doing in line number 6. And if you don't do this, if you don't see this, if you pass in only an integer or something like that, then we get these long page-wide errors, and it's hard to reason what we just did wrong. Okay, and we once again have to look into the implementation of do-locked what this parameter t, or in the case of the function parameter f, does here. And this is what we can change with C++20. I can remove the template head because I can use abbreviated function templates. Like you see it in line number 1, there you can see auto. And I showed this on a couple of slides before. We are looking at a constraint placeholder type here because we can use a concept stood invocable to limit this type here and to talk to everyone using this function, telling them that f must be an invocable. Nobody no longer needs to look inside a function body. It's there in the function signature. And this is what makes concepts so great, so beautiful, because this is documentation. This documentation you can see, you can understand, and the compiler sees and understands and checks. Okay. You can, of course, also use this invocable in the template head instead of type name t, but for this example, I did want to get rid of the template head entirely. So there's, aside from function templates, when I talk to people about concepts, there's one thing they tell me that they are most interested in, and this is error messages. So we are hoping to get better error messages from concepts. So this is the motivation here. Let me briefly walk you through this slide before we talk about error messages. What I'm doing here is I'm creating myself a type trait like thing called isContainer, which checks whether a certain type satisfies the requirements of the containers in the standard library, of a container in the standard library. Such a container comes with a value type, with a size type, an allocated type, an iterator type, and a constant iterator type. And it provides the member functions size, begin, end, cbegin, and cend. There may be more elements to a container in the standard library, but let's go with these basic 10 requirements, okay? And my isContainer checks that. And now it depends on how much you work with templates, how much you know about all that things that are on this slide. Let's step back and think about it like we are beginners. We see code like this the first time, but we know C++, we know a couple of rules. So there's one definition rule. We should have the same name only once. But here in line number 5 and 2, I'm seeing isContainer. That's odd, right? Of course, then I can learn that line number 2, that's the primary template, and line number 5, this is specialization. Yes, I can learn that. It's not nice, but I can do that. And then I have to learn what this stood void teasing in line number 7 is. I does practically nothing. Yes, that makes sense. What? Yeah, okay, there's nothing. Sure, sure, sure. Oh, line number 12 to 16, an awful lot of repetition, decal type and decal wall all over the place. And what was decal type doing again? And this decal wall thing, can you remind me? Oh, I have to learn that, right? I'm happy to teach you that, but I'm more happy to not teach it to you because for this example here, it looks really not like something yeah, we should have to write from a beginner's perspective. And then, oh, that's also nice. Line number 2 is container derives from false type, and line number 17, my other is container that derives from true type. Okay, I may have to learn what this false and true type thing does, but shouldn't they have the same parent thing? Yeah, that's odd as well. But of course, we know because it's a primary and the specialization, they can be different and so forth. But it's not easy to understand as a beginner. And then line number 21, I'm testing my concept with a struct simply A, which has nothing of these methods or types in it. And then there is this colon value thing. And where does this come from? I don't see it on this. Oh, yeah, you say it's from the false type or from the true type. Yes, that makes sense. Okay, it only costs me probably a week, a month, or more than that to understand all these components on this slide. Maybe you get it in 1 hour, I don't know, but it's too much, regardless of how much time it takes you individually. So it makes me cry. Okay, it's good that we could do that in the past, but it wasn't nice. This is how it looks in C++20. In line number 1, I have the template head. Line number 2, I'm creating myself a concept. I'm calling this container. This follows the regular pattern in the standard library. And then I'm assigning a requires expression to it. And now on line number 4 to 8, we see the one requirement kind I haven't talked about previously. This is a type requirement. And it practically checks that in the namespace of T, there is a type called value type. Not only a simple, it must be a type. And we start a type requirement with type name in front of it, okay? And then there are so many good parts. So the true and false type thing is gone. This miserable inheritance is gone. I don't violate ODR any longer, which I didn't before, but it looked like that. And the decal type and decal wall thing are gone. And this void T thing is gone. But line number 9 to 13, that's beautiful. T.size, T.begin, and so forth. This is readable code. This is code like we write it outside of templates. And we are able to do so because of the requires expressions power to define in the parameter list a parameter which we can refer to. And here I'm simply saying that my parameter is of the capital T, so the type that this concept is called with, and I'm creating myself a lower T parameter, and I'm using that one later like I would do in a function. And that makes that thing so much more beautiful. And line number 18, the colon value thing, that's gone. We don't need it any longer. This is the power of concepts, okay? This is readable code that's easy to teach, that's easy to read, it's easy to write. That simply makes me cheer, okay? That's concepts, that's great. But I promised you error messages, right? So let's step back a moment and switch to Compile Explorer and see how we are doing on the error message front. This here is the code from the slide. The only thing I changed is I'm having another check here whether my isContainer concept works with a std array of type int of 5. And currently it doesn't. I negated it. And this is the C++17 version. Once I remove the not, then, well, the static assert tells me it failed because of the requirement is container, value. That's a big surprise, given that's the only thing that's checked in the static assert. Yet it doesn't tell me why it fails. Can think about it. Maybe you know it, maybe you don't know it. If you know it, think about std_array may be a type in your new project where you don't know all the details. So C++ 17, it's all right. It prevents us from shipping it to customers, but it doesn't help me finding the error. This here is C++ 20, the concepts version, same thing. I remove the not and I see, oh boy, yeah, the static assert failed. All right, I expected that this time. And here is then a note, because std_array does not satisfy container. All right, that's as helpful as before, but now the third thing that tells me, because type name t : allocated type would be invalid, because there is no such type in std_array, and I also got these quizzling marks beneath my allocated type. And of course, the purpose of std_array is to have the memory allocated at compile time as a fixed size array and no dynamic memory, so we don't need an allocated type. Yeah, now the compiler tells me the exact reason for why it fails, and this nice and short. So not only is this code in C++ 20 easier to write and easier to read, the error messages are better as well. So thumbs up, we can cheer. This is a real good improvement, okay? But there are other things in C++ 20 that improved when we are looking at templates. Let's look at non-type template parameters. We now are able to use floating point types as non-type template parameters. In this example, I'm creating a function fun, which takes a double as a non-type template parameter. On the line number 6 and 7, I'm calling it. And they can call it with, for example, a plus 0.0 and a minus 0.0. So we are preserving the mathematical correctness at this point of the floating point value. I never needed the difference between a positive and a negative 0. For me, it's always 0. But there are areas where it makes a difference. And there's something that you probably should know about this, and this is the following. So if we look at this in Compiler Explorer, this is the code from the slides. And then we can see here in this call, the part of the instantiation of this function template, that's all zeros. While the other call, that's fs and zeros. So the first one is the IEEE 754 representation for the positive 0, while the latter one is the one for the negative 0. And we can see that we get two different instantiations of this function template. And once I remove the demangling of the identifiers, we can see that the value of this non-type template parameter that goes into the mangled name of the function template. And this is why plus and minus 0 result in different instantiations of the function template, which it will do for every positive and negative number, but for 0, it's maybe the most surprising one. So we're preserving the exact same semantics, but you have to be aware that plus and minus 0 are different things now, which is what most people wanted at this point. So aside from floating point numbers as non-type template parameters, we can also have class types if they satisfy certain requirements at this point. And here is such an example. I do have a class template called fixed string. It takes two template parameters, a char t, which is a type parameter, and the size t, which is a non-type template parameter. And I'm using these two parameters to create in line number 3 an array of char t called data of size n. And then in line number 5, I'm creating a const export constructor for fixed string, which takes a reference to an array of type char t of size n. And I use copy n to copy all the data from the parameter into my local member variable data. And then on line number 8, I can create a variable of type fixed string, call it fs, and in the curly braces, I pass the string hello, C++ 20 to it. That's great, right? And indeed it is, because we adjusted some minor things about CTAD at this point, but it doesn't have really anything to do with non-type template parameters at this point. That's true. But this was the base for it. Here is using non-type template parameters for templates in C++20s when there are classes. Line number 1, I'm creating a template head which takes a fixed string as a non-type template parameter. This is the type we created before. I name it string or str. And my struct here, my template struct, is called fixed string container. It contains a method in line number 4 called print. And in there, I'm using std_cout to printing out str.data. This is the reason why data previously was public and not private. I want to have this example as short as possible. And now in line number 10, I can say I create a fixed string container, and in the angle brackets, I pass the string hello, C++. And this is the first time that we can do this in this neat and concise way, okay? Because we are really passing this string to our fixed string container, and we don't have to use any static helpers or things like that. And then in line number 11, I can call fc.print, and I will see printed out the string hello, C++ at this point. So this is a really interesting improvement, which will help us to explore new ways to formulate generic code in C++20. Whenever we talk about C++ and modern C++, something is there that, well, has space in each and every talk, I guess, and that's lambdas. And we are talking about templates here. So since C++14, we can have generic lambdas. So generic lambdas, they carry the auto in the parameter. And what I'm doing here is I have this variable called max, and I'm assigning a generic lambda to it, which takes two parameters, x and epsilon. And inside, it does what the name implies. It checks whether x is greater than epsilon, and if so, it returns x, and otherwise it returns epsilon. You should use the STL version, the algorithm there. This is just for making a case here. And now I can use max in line number 7 and 8 and call it with 2,3 and 2,3.0. And line number 8, it's what's bothering me. Because remember from the beginning, I don't want mixed types. That leads to awkward situations and sometimes to errors, or often to errors. But there was no way in C++14 or 17 to say that we want our lambda to take a parameter of any type, but those function parameters or lambda parameters should be of the same type. And there was a hack, but that's not really nice. So I wasn't able to formulate this in C++17. And I'm now, because C++20 gives us lambdas with a template head. And this makes lambdas fit even better into the language. They're more to becoming first-class citizens here because there are no more exceptions or less exceptions than previously. So what I have here is I still have on line number 3 my variable max. And then after the capture clause, we see the angle brackets, and this is my template head. This is the only time where it goes without template in front. And in these angle brackets, because it's a template head, I can specify a type parameter and non-type parameter. I can use concepts there. So this is the full-fledged template head just without the template. And what this enables me to do is to say that my lambda takes a type name t, and I use this t for both the parameters x and epsilon. Now, line number 8 still compiles, but line number 9 will be rejected. And the reason for that is that there are no implicit conversions when it comes to templates. And because x and epsilon must both be of type t, compiler tells me, I don't know what type t in this case is because it's int and float, if you're looking at line number 8. So this is another nice piece where lambdas got improved in generic code. And here are two things how you can use this to give you something to think about. In line number 1 at the top, I create myself a lambda called lamb. And of course, it's a lambda with a template head. It takes a type named t. And as the parameter of this lambda, it takes a std vector of t. Okay, that enables me to call this lambda with a std vector of int called v in line number 4, but I can no longer call this lambda with just the number 20, like in line number 5. And that's really great. And then line number 1, a lambda lamp. In the example at the bottom, it takes a size t, so a non-type template parameter. And this enables me to say that my lambda now takes a std array of int of size n, and the n is the non-type template parameter. In line number 3, I'm declaring myself a std array of int of size 2, call it a, and now in line number 5, I can call lambda with a. And that's the beauty here. I cannot call this lambda with a std array of type char of size 2, for example, only of int and any size. So like with function templates, we can do the same things now with lambdas, okay? All right, this was a preview, I would say, into C++ 20's templates and concepts. There's much more to talk about when it comes to concepts. I hope you enjoyed it. I created a C++ 20 concepts cheat sheet. You can go and subscribe to my newsletter to get it. I also wrote a book, which I recently published on Amazon, Programming with C++ 20, where I think I have 40 or 50 pages about concepts. So if you want to learn more about this and of course the other features, go give it a try. I hope you enjoyed it, and all that's left for me to say is I'm fertig. Thank you. Are there any questions? Let me check. So the question here is, do you have any examples of usage of concepts or templates more generally? I can't figure out except in a case of a very generic library. Oh, so you're asking me where and when to use concepts or templates. Well, that's rough or hard to say. First thing is, I would say, let's start talking about where to use templates, and then you can apply concepts there to restrict them. And I use templates a lot. All the time when I have patterns that are similar, I try to come up with a template, because then I have to write this code only once. But I think we need to see code or samples of your code base to show you exactly where you can use them. So out of the blue, I don't have a really good answer to that, where to start using templates.